Now I am plotting a complex exponential signal. This is a complex exponential signal. See, we have studied in a Fourier transform like e power j omega t. How will that e power j omega t be visualized? How to visualize that e power j omega t? So this is a very good visualization of e power j omega t. Time domain, you know, e power j omega t is a complex signal. You have real term and imaginary term, right? So you see, I am plotting with the three axes: time, in real term and imaginary term. And what is modulus of e power? When you take absolute value, what is the modulus of e power j? Can somebody say the answer? What is the modulus of e power j omega t? What is the modulus of e power j omega t? When you take modulus to e power j, what will be the answer? E power j omega t is, yes, very good. The answer is 1. So the maximum value is 1, the minimum value is -1. Because e power j omega t, I can write it as cos omega t plus j sin omega t. Cos will vary from -1 to 1. Sin will vary from -1 to 1. Cos will be my real term. Sin will be my imaginary term. So you see the time domain graph. And you know e power j omega t represents rotation. It will rotate from 0 to 360 degrees. So you can see rotating circles moving. This is the basis for your electromagnetic waves. And you are representing electromagnetic waves by e power j omega t, right? Why do we represent? Why do we add a component e power j omega t in electromagnetic waves? Because those waves will rotate and move. You see here, the e power j omega t is starting. E power j omega t is starting from 0 and it is continuously rotating and moving. You see, as the time is going to move, the e power j, the signal is rotating and moving. Okay, so this is an excellent example of your e power j omega t signal. And if I want to plot the frequency response of this signal, what is the frequency response? This is the frequency response. See the frequency response. E power j omega t. What is the frequency? The frequency is 1000, and you see at 1000 you see a peak. That's all. So all the complex rotating signal in time domains becomes a simple signal in frequency domain. Is going to be 1000. At 1000 you have a peak. Simple. You are able to. This is the Fourier transform. See how Fourier transform is simplified in MATLAB using just 5 lines. It is very, very simple. Please understand this. I'll again say I'll share all these code snippets with you. You need not worry. Whatever project you are doing or if faculty members are there, please run all these codes and show to students how signals look like in real time. That is how they will be motivated to learn more from you. They will be eager to learn more from you. Okay, so that is my humble request to all the faculty members who are attending this section. What happens if I add one more signal? If I add one more signal, e power, without disturbing, I'll just copy paste this. I'll add one more signal so that we'll see how it is working. I'll add 2000. So now I have two frequencies, 1000 and 2000. We'll see whether the answer we get two peaks at 1000 and 2000. You see here, as you add one more signal, the pattern in time domain is changing, but still it is rotating and moving. Because I have two signals, right? So when you add them, it will not be a proper circle. So it still rotates and move, and you see here two peaks at 1000 and 2000. This is the full frequency spectrum. In Fourier transform, whenever you do Fourier series, you will be finding out magnitude spectrum and phase spectrum, right? So what we have got is the magnitude spectrum. You get two peaks, beautiful peaks at 1K and 1K and 2K. Okay, so this is what I want to demonstrate. And